So hello everybody, once again, welcome to Design 2022. I hope that you enjoyed presentation so far. Now it's your turn to amaze audience and to see what your colleagues are doing and to ask questions, the naughty ones, of course. So the schedule will be as follows. I will shortly introduce each speaker and then we will play his presentation. And after all the presentations, we will have a discussion and questions. If you have any question during the presentation, be free to put it in chat and I will read it later and we'll discuss it. And of course, after presentations, if anybody of you or audience would like to ask questions in live, that's okay. Is anybody have any questions? No. Okay. The first presentation is from Michael Schlegel. He is from Karlsruhe Institute of Technology from Germany. And in his CV, he stated that he is currently a research assistant at that institute and, of course, in Institute of Product Engineering at Karlsruhe Institute of Technology. So let's hear his presentation.
So, hello everyone and welcome to my presentation. My name is Michael Schlegel. I'm a research assistant at IPEC Institute of Product Engineering at Karlsruhe Institute of Technology in Germany.
I guess.
Today I'm going to present to you a study I did together with my colleagues.
Sorry, you said there is no sound, right?
No, the sound is just fine.
Somebody mentioned that there is no sound.
Okay.
I will continue playing the presentation. Please let me know if you had issues. Okay.
So, hello everyone and welcome to my presentation. My name is Michael Schlegel. I'm a research assistant at IPEC Institute of Product Engineering at Karlsruhe Institute of Technology in Germany. Today I'm going to present to you a study I did together with my colleagues on implications of creating solution concepts based on the use of references. The development of new products does not start on a white sheet of paper. The model of PGE describes product development based on two basic hypotheses grounded in practical experience. This example of a LED light bulb shows each product generation is developed based on references and with three types of variation. Our research environment is the course MSUP, Mechatronic Systems and Products, in which one team is divided in two groups and is going to develop a real complex mechatronic system. On the right-hand side, you see the collector, which collects the cubes on a playground and transfers them into the stacker. On the left-hand side, you see the stacker, which stacks and sorts the cubes from the collector on two towers. The two systems are operating completely autonomous. In context of the course MSUP, we can use the documentation of the previous year and adapt it with principal, embodiment, and carryover variation, so the existing solution concepts of the previous year are used as an internal reference. How exactly the references are used in the workshop can be seen here. As shown in the upper left corner, subsystems can be taken from the internal reference products. Below is an example of an external reference product, a cargo conveyor system, so elements to develop solution concepts can also be taken from external references. As the state of research shows, new products and systems and their solution concepts are developed based on references. It is necessary to investigate what impact the use of references in the development of solution concepts has on partial solutions, the evaluation and the representation of solution concepts, as well as what problems developers face when developing solution concepts based on references. Therefore, our research questions were, what are the impacts of using references to develop solution concepts, and what are the challenges in creating solution concepts using references? 2019-2020, selected potential reference products were provided, but the developer stated that the number of references was not sufficient to estimate and use them in a target manner. To address this finding, the scope of references was significantly increased, and comprehensive references in the form of project documentation from the previous 2 years were made available in the 2020-21 cohort. The 2020 cohort developed based on a few references, whereas the next cohort had access to all available references from the previous 2 years and had to identify appropriate reference system elements on their own. To answer question 1, we analyzed solution concepts in the milestone presentation of the development teams regarding the system view, the functional view, and the physical view, and the embodiment view and the use of references. To answer question 2, we did an online survey and interviews. The indicators for the use of references indicate a clear change towards a more extensive use in the 2020-21 cohort. The use of references in the solution concepts is shown exemplarily in the figure 5. On the left is an example of the 2019-2020 cohort with no explicit documented reference system elements, and on the right an example of 2020-21 cohort with significantly more linked reference system elements. The illustration on the right also includes an initial assessment of risk, benefit, and development effort of the subsystems based on the references considered. Furthermore, the share of CV, EV, and PV was indicated for the generation under development. The comparison showed that functions were named explicitly and more often in the 2020-2021 solution concepts. Based on the naming of functions the system has to fulfill, the function view is more pronounced compared to the previous year. The example shows that the functional analysis results of a team in 2020-21 cohort. According to this, over 50% of the functional failures were due to the two main functions. Comparing the physical and embodiment view, it could be observed that the ratio of concept representations using principal sketches, photos, and CAD models has changed. In the previous year, 86% of the illustrations are assigned to principal sketches and only 14% are distributed between photos and systems of illustrations of CAD models. In the year with more references, 45% of the illustrations are principal sketches and 19% of the illustrations show real systems with embodiment information. 86% of the illustrations in the year under review show CAD models. This represents a shift towards more embodiment information in solution concepts in the 2020-21 cohort. According to the developers, risk and benefit could be better assessed based on references. The assessment of the effort required for the development showed no significant improvement. Let's take a look at some of the challenges we encountered when using references. First, developers indicated that looking at references restricts their creativity. Second, the developers indicated that they preferred to implement their own ideas and solutions even though they were aware of the higher risk involved. To summarize, the development of solution concepts using references increases the level of embodiment information and also a higher amount of already validated subsystems. It leads to a more detailed and critical functional understanding. We also observed that the students name the tension between creativity and the use of references, the adaptation of other people's ideas versus realization of own ideas, the right amount of available references. So the last 3 points represent key topics for the future research. So thank you for your attention. I hope you enjoyed the presentation. You are always welcome to reach me via our institute homepage or also via LinkedIn.
Thank you. The next presenter is Stefan Plappert from Leibniz University, Hanover, from Germany. As CV says, he's currently research assistant at Institute of Product Development at Leibniz University of Hanover. So we will now hear his presentation named feasibility evaluation of milling designs using multi-agent systems. Go.
Dear ladies and gentlemen, welcome to my presentation with the title Feasibility Evaluation of Milling Designs Using Multi-Agent Systems. My name is Stefan Plappert. I'm a research assistant at the Institute of Product Development at the Leibniz University of Hanover. My presentation is structured as follows. First, I will explain the usage of multi-agent systems for decision-making and put it into the context of engineering design. Then, I will present our approach to a multi-agent system by explaining the architecture and the application to a gearbox housing. And finally, I will discuss our findings and conclude them. Imagine the following situation between a design engineer and a manufacturing engineer, as it might occur every day in the production of milled parts. The design engineer designs a component to the best of his or her knowledge, and after the design has been completed, he or she hands the CAD model over to the manufacturing engineer. The manufacturing engineer checks the model and finds that the pocket cannot be finished with the existing milling machine, as the cutter cannot produce sharp corners. This means that the engineers have to communicate with each other and negotiate how the problem is to be solved. Either the design engineer adjusts his or her design because he or she knows the exact function of the component, or the manufacturing engineer has to use a different manufacturing process. The clarification and subsequent implementation lead to a delay in the manufacturing of the component. Wouldn't it be better if these errors could be avoided during the design phase by having a second design engineer or the manufacturing engineer review the design at an earlier stage? This would again lead to more effort, and there is no guarantee that all errors will be found. For this reason, our approach is to digitize the 4 I's principle by proactively supporting the designer with the help of agents and checking his design directly in the CAD program. To do this, we analyze the 3D product model based on the stored manufacturing knowledge and automatically adjust the CAD model. The beginnings of the development of IT solutions based on a paradigm of distributed artificial intelligence and program agents date back to the 1990s and are still relevant to research on agent-based technologies. Although the term agent is only loosely defined in literature, it can be agreed to that an agent is a computer system capable of autonomous action in its situated environment to achieve its dedicated goals. A multi-agent system consists of a number of agents which interact with one another, typically by exchanging messages through some computer network infrastructure. The basic idea for networking agents is that they cooperate in solving problems, share knowledge, work asynchronously, are modular and robust through redundancy, and represent multiple viewpoints and expertise of experts. The multi-agent system for design evaluation of milling designs is based on the math platform Spade. A major advantage of Spade is that it's programmed in Python, as it contains numerous artificial intelligence libraries and thus offers interesting extension possibilities for the math. Furthermore, it is FIPA compliant and the agents communicate via a communication server through which the user can be also integrated via Messenger. For the evaluation of CAD models and decision support for designers, an interface to a CAD program has to be provided. Autodesk Inventor is used as the CAD program since the BREP of the CAD model can be accessed via the application programming interface. Each agent is itself a knowledge-based system, so the required knowledge in the form of standards or tool lists is stored as a relational database in Excel spreadsheets. As an application example, the CAD model of the gearbox housing, which is completely machined on a milling machine, is analyzed. The evaluation of designs contains individual work areas which are divided among experts. Based on this, the tasks are distributed to the agents according to the topic. For this purpose, the feedback agent is responsible for collecting and then passing on the information to the user. The information from the CAD model is read out and transferred by the info agent. This information is used by the design agent to request features from the user via Messenger. If the features were only inserted for aesthetic reasons, they are suppressed in the CAD model and disregarded for further evaluation. The manufacturing agent is available for planning the manufacturing steps. This runs through all the features in the feature tree in the CAD model and checks whether they are combined into one manufacturing step. These manufacturing steps are stored in an action item list. With this information about the machining and the tool list, the tool agent is responsible for selecting the tools. The optimization of the tools is taken over by the planning agent. For the application example of the gearbox housing, the review by the MAS revealed the following possibilities for improvement. The front chamfer and the rear rounded edges were removed after consultation with the designer. The missing radii were added to the pocket on the front left side. In addition, the tool outlets on the top and the right front side were also added. The presented MAS offers a first step for the evaluation of CAD designs about virtual design reviews or the digitizing of the 4 eyes principle. In addition, the system can be used to simplify and digitize the approval process by allowing the reviewer to use the action item list for review. However, the existing system covers only a part of the design review, since on the other hand, the specific product requirements have not yet been implanted, and on the other hand, only formalized expert knowledge is used for the assessment. It was shown that a multi-agent system can be a promising tool for evaluating CAD designs, as it represents expert knowledge in a decentralized way in the form of agents and can be easily maintained and extended due to its modular structure. For further research, the focus will be on representing virtual design reviews with MAS. For this purpose, requirements need to be operationalized so that they can be used by the system and to evaluate the product fulfillment of these requirements. This is the end of my presentation. I would like to thank you for listening.
Thank you, Stefan. Okay, the next is Raudberget for Jönköping University. There is an echo in the. Do you okay or no? Okay, video presentation and we will talk later. So, Mr. Raudberget, Maya, please run.
Welcome to the presentation of our paper, Knowledge Reuse During New Product Development, a study of a Swedish manufacturer. The authors are Raudberget and Paraskeva Wlazlak from Jönköping University, Sweden.
In the context of new product development, knowledge reuse is perceived as important but also challenging, especially when companies grow and become more digitalized. Although companies may possess a great amount of knowledge, prior studies have identified barriers that might hinder reuse. Barriers can be related to one of the following categories. They can be related to people, to organizational structure and management processes, as well as to technology. This is according to prior literatures. Barriers related to the category people may occur because of, among others, individual might have a low awareness of knowledge repositories and existing documents. Individual might be, for example, overloaded with information, or, for example, time pressure could be a factor that limits the opportunities for an individual to search information, etc. If we take the category organization and management, so barriers that are related to organization and management may emerge because, for example, lack of leadership, encouraging, enabling knowledge reuse. Also, organizational structure processes used in the past and could hinder knowledge reuse in today's organization, or organizational culture also could be a factor that could hinder knowledge reuse. Barriers related to category technology information and communication technology might emerge because, among others, inappropriate technology integration that does not reflect individuals' needs might hinder knowledge reuse, lack of compatibility, integration between systems, or, for example, use of a complex technology. Because of the barriers, companies need to adopt proper organizational structures and also take actions in order to manage knowledge. In prior research, for example, A3 reports has been described as very important. They have been described as a means for capturing, organizing, and also reusing engineering knowledge.
The paper has two objectives. Firstly, to outline barriers that hinder effective reuse of codified knowledge. The second is to suggest means to overcome these barriers. The method is based on a case study at the large Swedish manufacturing company, starting with interviews with 8 different roles and then ending with 8 workshops with a core team of engineers and managers, clarifying the state of practice for knowledge reuse, and to introduce different methods around different knowledge management themes.
The empirical findings showed in total 9 barriers that hinder reuse of knowledge during new product development in the case we investigated. And we also identified that 8 enablers from the PLM system that can support knowledge reuse and enablers related to the A3 reports. And here comes some example of our empirical results. If we look at for example, one of the barriers that we outlined was the lack of clear ownership for document administration. Some respondents expressed that in many cases there was a lack of clear responsibility for revising and reviewing documents. It was not clear who administrated and updated documents, and often the responsibility was on the individual that has created a certain document, and has a document were managed by individuals rather than by group of a team. Yet another barrier was related to information scattered in different systems. If we take the second barrier, so many documents that contain related information was created, as well as documents could be found in different places or systems in the organization, and this makes it difficult to find the right piece of information. And it also created confusion as to which source of information an individual could trust. Yet another example from the barriers that we identified from our case was content and structure of codified engineering knowledge. This was related to the fact that changes in a completed development projects did not include history of the rationale for making a certain design decisions, which resulted in a repetition of old mistakes when new products were designed.
Suggested structure for integrating A3s in PLM. When new knowledge is available, the A3 process starts. Begins with creating the A3 and then reviewing it by the peers. When it's approved, it's stored in the PLM system. Updates are crucial, preventing outdated documents from being a part of the knowledge platform. If an A3 is deemed as being okay, a new timestamp is given by the PLM system so the users will know that the document is still valid. When a person needs knowledge, the context will be identified in the PLM system depending on where the user is. It could be accessing from within a CAD system, from process descriptions, or through hyperlinks. This will narrow down the search. The user is now provided with the content in the form of a list, abstracts of the retrieved documents, and the user can choose which one to continue with. To conclude the presentation, the focus of this paper was to outline barriers that hinder effective reuse of knowledge and suggest possible ways forward. The contribution is an approach that combines A3s and a PLM system to pass the identified barriers. The company has introduced A3s as a knowledge management tool in one design department and is currently working on implementing those in the PLM system. Thank you for your time. For questions, please contact us on our mail addresses or scan the QR codes.
Thank you. The next presenter is Mr. Kevin Eder from Mercedes-Benz AG. I think he will, in his presentation, tell something about himself. For now, I only have information that he received his master degree at University of Munich. So let's hear what he has to say.
Hello, everybody, and welcome to my presentation about knowledge documentation based on automatic identification and clustering of change intentions in CAD data of wiring harnesses for the 17th International Design Conference. My name is Kevin Eder, and I'm happy to present you our work in the next few minutes. First of all, I want to give you a little outline of what I want to present to you within this presentation. I'm going to start with the motivation for this work. In the second part, I want to present you our methodology, followed by its validation. At the end of this presentation, I'm going to give you an outlook for future work. So let's start with the motivation of this work. Due to the high complexity of the wiring harness, both in development and production, specific timelines have to be met. For example, in order to ensure an on-schedule installation of the wiring harness into a physical prototype, it is necessary to start creating the drawing, subsequently manufacturing the wiring harness before the data freeze of the specific development phase. Since the development of the overall vehicle for the corresponding phase is still ongoing, further adjustments of the wiring harness have to be done. Since these adjustments, respectively the specific knowledge, can be relevant for the following development phases, they must be carried out several times. To address this, we've presented an approach for a knowledge management system in the past. With this system, changes being made to a CAD model are documented, transferred, and reused into other CAD models automatically. To advance this approach, I will focus on the knowledge documentation today. In order to transfer changes efficiently, the corresponding knowledge have to be extracted and processed. Therefore, changes have to be detected first. Subsequently, all changes have to be clustered according to their change intention, thus increasing the reusability. Furthermore, the knowledge has to be documented for the following processes. In addition, a change description should be generated to make the contained knowledge more comprehensible for potential reusers. Now let me show you our methodology. In order to detect the changes automatically, we had to make the knowledge contained in CAD data accessible. Therefore, we have analyzed the structure of a wiring harness CAD model, which is a tree-like structure and built by many individual segments. Due to its modular structure and the clearly defined linkage of each element, a wiring harness assembly can be fully described by the knowledge about the part data, the associated information like the electrological function of the connector, their positioning, as well as the routing path of each segment. Since the main aspect of the wiring harness development in CAD is the routing and connecting the components, the change management of the individual library parts, such as the connectors themselves, are not relevant for this approach. Therefore, we have specified a knowledge representation using an XML scheme, which can be exported via API from the corresponding CAD application. Afterwards, we have analyzed all change scenarios which can be made to a wiring harness CAD model. For example, changing the position of a connector, adding a fixing, deleting accessory, or changing the length of a wire protection. Based on that, we've linked each scenario to the corresponding attributes of the knowledge representation. This enables a rule-based detection of each change scenario in an automated way. Since many independent changes can be executed by the designer between two incremental versions, it is necessary to separate those changes from each other and cluster them. This increases the potential reusability of the corresponding knowledge. Therefore, specific rules were defined. For example, each segment is handled as an independent cluster. If a change affects the node, the adjacent segments are joined into one cluster. The knowledge documentation serves to store the gained knowledge. Therefore, an XML scheme called diffXML was specified, containing information about the previous and the new state. Datasets that match with the previous state can thus be identified as potential reusers. Furthermore, this scheme allows an automated generation of change descriptions using predefined text modules. Based on this, potential reuser can decide whether the corresponding knowledge is relevant or not. To validate our methodology, we have used a CAD model of a wiring harness in which different and globally distributed changes were made. Those were chosen so every change operation and every element was used at least once. For example, adding a segment, deleting, fixing, and so on. The individual changes were detected, clustered, and documented successfully. For example, in cluster 3, the connector has changed its position, and in addition, the segment has changed its routing and length, as well as the bifurcation has changed its length. At the end of this presentation, I would like to give you an outlook for future work. Future work will investigate how the presented knowledge documentation can be used to detect potential reusers automatically, and how the knowledge can be integrated into other CAD data models. Thank you very much for your attention. If you have any questions, feel free to ask. Otherwise, you can contact me under the displayed data. Thank you very much and have a nice day.
Well, thank you for presentation. The next presentation will be held by Christoph from Karlsruhe Institute of Technology. As I can see, Mr. Kampf started his assistant doctorate at the Institute of Product Engineering in September 2019, and he's, I assume, currently working on his PhD. So let's hear his presentation.
Hello and welcome to my presentation. My name is Christoph Kempf. I'm a research assistant at IPEC Institute of Product Engineering at Karlsruhe Institute of Technology, Germany. And I'm going to present to you a study I did together with my colleagues on identifying factors influencing the design of a suitable knowledge base in product engineering projects. We all know the iPhone, and I guess we all can agree that the iPhone was and still is an innovation having a huge impact on our lives. But was the iPhone totally new? Well, as it is, yes. But as Steve Jobs said himself already at the introduction, it is a combination of technologies and subsystems Apple already knew. It takes reference on the iPod and iPad for shape and touch control, other smartphones of competitors for the network technology, and their iMac for the operating system. In other words, Apple had the right references at hand at the right moment to innovate the iPhone. The big question now is, can we actively predict and choose the right references to support the development of new successful products? That's the main question that motivates us conducting our study. Let's start with some basics. Every product development process is unique and a subsequence of various product engineering activities. Albers et al. Developed the IPEM, Integrated Product Engineering Model, to model such product engineering processes. We use this model as a starting point because every activity will have a different focus on characteristics of a knowledge base. On the other hand, Albers et al. Describe product engineering as a process of developing a new product, such as the first iPhone, based on an already, at least mentally, existing knowledge base, the so-called reference system, which summarizes already existing or planned elements that form the basis and starting point for the development of new products. Based on these two concepts, we started our study with the objective of describing the correlation of influencing factors of product engineering on the design of reference systems. Therefore, we formulated the following two research questions. First, which factors in the context of product engineering influence the reference system? And second, how can the correlations between the identified influencing factors and the reference system or its elements be described? To answer these questions, we started with a literature survey of knowledge reuse based on the publication introducing the reference system. Additionally, we analyzed case studies of my institute, supplemented with case studies of product development projects described in literature by conducting a systematic literature review on Scopus. And to sum it up, we analyzed various process models established in product engineering. In the end, we collected 19 different factors that were described having an impact on the use references or the design of the reference system, such as the targeted development time, activity of product engineering, or the experience of the individual designer. Analyzing these factors, they could be clustered in two groups. Factors such as the protection status of references, such as patents, or the level of standardization within the company that directly influence the reference system. And on the other hand, there are indirect factors such as the industry or the type of company. Analyzing these factors even further, they can be categorized within four context groups. Here we have factors coming from the market, the company itself, project-specific factors, and factors related to the humans and team involved. This made it apparent that factors in the market and company categories tend to be indirect factors, while factors in the project and team or human groups are more often direct influencing factors. Summing this up, we constructed this interrelation model, which depicts all the influences and even more matches the influences to the right column, which shows the reference system and characteristics of the reference system elements and the reference system as a whole and the influences. In the end, we were able to confirm that various engineering situations as combinations of, for example, the context and position of the company in the market, industry, current product engineering activity, and team composition require different characteristics of the reference system or its elements. However, that does not suffice for general statements of how to adjust or design the characteristics of the reference system and its elements, but provides possible best practices. It's very important to remember that these factors cannot be considered individually because of their interrelations between each other, and therefore all the factors have to be considered as a system. Nevertheless, we expect our model to be incomplete, and thus each development situation should be analyzed carefully to derive possible implications on the reference system or its elements and adapt the interrelation model accordingly. But still, we believe with further extensive literature review and combined with surveys to evolve the model even further, we can develop a supporting method for product engineers to design their project-specific reference system. Thank you for your interest, and I'm looking forward for many interesting discussions.
Thank you, and thank you all for your presentations. They are very interesting, and as I can see, we all struggle to keep record of the knowledge of our companies and engineers in various industries and domains for the future reference and for future use, and all your works in that area, and there are good examples in different parts of engineering knowledge that have to be saved and deal with. So first of all, I will ask you all if you have any questions. We will start with Mr. Michael Schlegel. So if anybody has a question for him. Question? No. Well,
I have a question. Yeah.
Yeah.
The reference system, as we heard in 2 presentations at least, what are the requirements on the references? Because I guess there will be a lot of references if you just have a lot of product to reference. Yeah.
There are no. Yes, there are no clear reference, but first of all, thanks for the question. There are no clear it's more like how nearly the reference products and the reference system elements are to the generation I want to develop, more as the special kind of reference. So I need some embodiment information, some information of the function of the reference system element. So if it's kind of in future research, I can't use it. But if it's a product of another company, I can buy it and I can analyze it and I can use it as a reference.
Thank you.
Okay. I have a following question, and it's from the last presentation that your colleague asked himself. So I will ask you how to choose the right references. He is trying to give the answer. How did you do it?
So the question to me or Mr. Kempf?
Oh, no, for you, because he is trying to answer the question, but you used the same reference model, but you didn't address it.
So I don't choose the references myself. The students did it in the student cohorts, and they choose like if it's risky to adapt them. Do they understand the function? Do they have the CAD models to these references? And how much effort it is to adapt these references into the new generation? These are factors the students regarded, yeah.
Are there any guidelines what to choose, how to choose it?
No clear guidelines, no.
Just the common sense.
It's mostly common sense, and you can differentiate between carryover principle and embodiment variation, and it depends on the share of principle and embodiment variation, if it's risky or if it's kind of like easy to use again. And that's the most significant difference in the use of references, yeah.
Oh, I see. To get back at your research, did you evaluate final concepts of the group cohorts from the 19 and 20 and from 2021 students groups?
Yeah, we evaluated them in the milestones and give them marks for each year. And yeah, we see significantly that the year with more references did more detailed concepts than the year before.
More concept, but what about the quality of concepts?
Yeah, the quality, also the performance is a bit better, but not significantly.
And that's all related to number of references used in later research.
Probably, yeah.
Yeah. What if references are, shall we say, the same number, but different, shall we say, quality? Is that relevant? Would that make any impact on result?
Yeah, this is also relevant. The students had also videos for the testings of the systems, of the reference systems. And with this documentation of previous testing, you get a lot of information of how they work, what is critical. And if you leave that information, or if you don't have access to this information, it's harder to use them and to choose which reference system do you want to pick.
Nice. Let me reference what you said and did with research from Mr. Kemp. He did also something about references, and in his research, he did some survey of articles about the reference system. So I'm asking both of you, did the reference system have any real industrial usage where you can draw some conclusions and some data?
Yeah, for sure. Probably every development is made with a reference system, but mostly not explicit. So it's kind of common sense that if I want to build a new car, I will take a tire from the last generation or a chassis from the last generation. So it's common sense and also still today practical. Yeah.
Okay. Again, do you have anything to add?
I can just agree on my colleague, on Michael. Basically, we, at our institute, there were done various studies on industrial cases. For example, the iPhone case I just showed, this is a retrospective case study we were doing earlier. Yeah, so far usually, you can find these interrelations between predecessor generations or already other existing systems within the same company or competitive products. And so you can explain or describe it. The reference system or the whole model of PGE product generation engineering, which is behind it, is kind of a descriptive model that you can use to describe this. And so far, for my knowledge, or I guess for our knowledge, to some extent, you can apply it on any case of product engineering or product development.
Okay, nice. I listened to some interviews from previous employees of Apple company, and they say that they don't share knowledge in their company as much as they would have, and they like to. So implementing reference system is such environment, it would be very challenging. Yeah. Thank you for your answer. Does anybody else have a question for anybody else? No.
Actually, I would have a question to Doug and Paraskeva. So thank you very much for your presentation. I really enjoyed it. My question would be, did you focus on internal documented knowledge only, or did you also consider other knowledge, like knowledge from other sources, from, for example, outside the company, or even from university research? And if so, are there other barriers, or is there other points to focus on?
Okay.
I can start. Maybe Eva could fill in if I misunderstand. But the focus was to use the knowledge they have inside of the company by better documenting routines and standard designs, like references and things like this. And we haven't considered the outside yet. I don't know if you have any ideas if that would be more challenging or create other barriers, maybe.
I have a question, a little bit counter question. Like when you say outside, what exactly do you mean? For example, documenting knowledge that comes from, let's say, some suppliers, or what do you mean exactly outside? I wasn't really, did not really get that.
Exactly. For example, from suppliers, from corporations, but also from competitors when doing, I don't know, a market survey or a benchmark of competitor products.
No, I think mostly, specifically in that case, then we looked at how to codify knowledge inside the company, because what they had the problem is to transfer, specifically that company was to transfer and reuse basically knowledge between different development projects, because what they do is that they carry out a development project, and then at the end they have some lessons learned and etc. But then it's very often that they unfortunately it's like this, that the next project starts and perhaps you don't use to the extent that it could be this lessons learned, so to say. So we wanted to in a way to that's why we looked into they work with the PLM system they have, so we wanted to somehow to standardize the way that can some general knowledge that can be applicable for a different development project to codify it and reuse it. So we have to summarize to sum up your the answer to your question was that no, we have looked more into how to structure their knowledge internally.
I would say that the word reference you use, would be more a positive way of saying rather than saying standards, because engineers don't like to, in my opinion, to use standards. We want to be creative and things. But the reference sounds much more nice, like you have more choice.
The right word.
So we might use that word further
and
on.
the thing is that I have a background in production, so we look a lot. We do like standardize ways to do things. So I like the word standardized solutions, but I could understand that perhaps it's not the best word. Yeah.
Okay, when we are on the subject of A3 and PLM, I have a question. Did you see any enablers in PLM that can enable also implementation of A3 to be the part of the PLM, not as you like you are creating A3 drawing or document and put it in the PLM as a document? No, but something that's actually live, dynamic, that have a link to visualization, to eventually some other document and so on. Did you find anything in that area?
I would say that the reason for using the PLM system is that because it's quite good at linking different sources, and like an A3 is just a short collection of words and images that is kind of, you need to be very accurate when you write it down, so not a lot of extra words and so on, so you need to focus on a subject. But then the challenge is that you will have a lot of A3s in the best of worlds, so that will be like not a gold mine. Maybe if you can't arrange them, it's the same with references, I guess. If you can't arrange them well, then you will have a pile of scrap instead of a gold mine, because you can't find things you're looking for. So that's why the 8th PLM system is quite good, because there's a lot of search methods, context things, and you can link from CAD, for example. Note in the standard CAD, the start model of a CAD, for example. And but there's also, to answer the rest of your question, our PLM person, his idea was to maybe generate the A3s from information in the PLM system. So when you need information, you don't actually write the A3s, but you have like a template. Then for certain things, you can generate these ones automatically for being readable by humans. Yeah, it's kind of a opposite way.
Yeah, I see that A3 has a potential. Definitely, it's from Toyota, but our students also use it as something like that, as a Blackboard EGPR, national European Global Product Development System. They all put their own knowledge there, and when you see the A3, then you see whole solution, and that's very nice. But problem was that it took them a lot of time, lots of effort to maintain the current state of the art of their product. So in a real environment, in this industry, you have not such luck that you have time to do something that definitely will be benefit for you or for others later on. And PLM has a unique ability to concentrate on and create, how should I say, like HTML, and you can aggregate information for PLM on one sheet, on one A3, and that can update regularly. If you change a drawing, your drawing on the A3 will reflect that change, and so on. So there is quite a lot of potential there, but I don't see any mechanism currently available that will make A3 creating possible right now.
Yeah. The company, they are employing it in a little larger scale right now as a pilot project. And of course, when you do it, when you start implementing things, you will find the challenges, such as when updating a document, the document will have a new number, and then we lose the references in the PLM systems. You need some still some hand work. I don't want to say in English. You need to fix some things before you can make it run smoothly. But there's a lot of potential, and of course, a lot of technology that you develop is not moving so fast. So say let's have you have an A3 of fasteners, for example. That could also be references like the other presentations. Well-known fasteners or stuff like that have been around for many years. They won't change a lot, and it's very important for engineers to if you have 17 different fasteners, which one should you choose for this maybe combination of materials. I mean, if you have aluminium or polypropylene or whatever materials and different threads and diameters, that's if we're able to do these design guidelines in A3 format, short and so on, rather than like the previous guidelines they had, like the screw guideline was 71 pages. I mean, that's it's not usable. But these shorter ones, if you can link them, that's I think it is one way to make it work. And then I agree, updating is probably quite hard. But now we at least have this automatic stamp to know when the document was approved late, when it was approved the last time. So you don't, yeah. It's a long explanation. Sorry.
No problem. So let me skip to Mr. Stefan Plappert. I read your paper. It was very interesting, especially thinking about multi-agent system and SPADE. But just one, shall I say, remark. Boundary representation is not what's in your paper set. The history-based modelers are built upon the boundary representation, but it's not the boundary representation. Boundary representation does not know the features. In a picture of your system, you have a extrusion and so on. I think just a little, bear with me a little bit. Like extrusion 2, fillet 4, hole 1, hole 2. That doesn't exist. Boundary representation. Boundary representation is points, connectors, and so on. So maybe you could change something further on in your. If you are writing something not in the native format of the CAD system, but in a neutral format, like STEP or IGES or VDFS, then you can say that that's similar, much similar to boundary representation than those of history-based model. Just remark, but it was very interesting.
I know. Let me explain you. You're perfectly right that the information is not in the BRAP model, but we used the BRAP model and read out the phases of the BRAP model and look, is this a curve? Is this a plane? And then we adjust that, and build, say, like our own feature. So it doesn't use the model tree in the CAD model, but the phases of the BRAP and read them out and look how we can manufacture them. And so it doesn't matter how the engineer models his CAD model with what features, and if he don't use the whole feature, then it doesn't matter to us because we use directly the BRAP information and the phases, and so we could also use additional information, like you said, from step files and something like that. But we originally used the BRAP structure.
Just as a thought, if you stick to the feature-based design model, did you think about the possibility to create a manufacturing feature that will be part of your feature? So when you are applying a hole to your product, then hole as a feature has a feature that's telling the system how it's done. So all the manufacturing information is inside the feature, like position at that point, choose that drill, then drill up to that hole, and so on. Did you think about that? Maybe.
We also. Then the engineer has to know the information how it will be manufactured, and we also use this system for teaching design students, and we want to analyze their CAD models, and so they're in education, and so we cannot expect them that they know how it will be manufactured, and so we want also use that for education, and
And that's nice for education. It's very nice. How you deal when technology is changed? When you, for example, switch from a regular milling machine to high-speed milling machine because the parameters of that machine are different. Are there a knowledge base that you store that information and can be used or retrieved later on?
Yeah, that's one application possibility because for the agents. So we can switch the manufacturing agent and also the knowledge, which is based on the agent which is based on that manufacturing knowledge. We can switch them or and use another milling machine. But right now we only look for 2.5D milling machines, and because free-form surfaces, very hard to extract and to analyze.
Yeah, that's right. Okay, thank you. Well, I have also a question for Mr. from Eder from Mercedes-Benz AG. I see that you are one of rare participants that coming from the industry, and you are dealing with a real problem. And I read your paper, and I was wondering how you achieve the saving or information saving that something is changed. Is it all in Siemens NX, or it's in different CID applications stored? You know, you're modeling something and you are done. And you said that information about the wiring harness have to be written in the XML file and change also. How that is accomplished?
Yes, thank you for your question. Our approach is to, for sure, we are using Siemens NX, and when we do check in the NX file to our PDM system, we are creating the XML file. Therefore, we are creating the diff XML file, which is similar to the software development, where we also have some kind of diffing files. And with the PDM file, we connect those modifications with other models where we might use them. For example, we have a wiring harness for cockpit, and we have them in different product variants, and we know, okay, there might be some changes that can be used in other wiring harness connectors, and then we check the XML file of those products and check, okay, if we can use them. So we have a PDM system and the backbone system, which checks the modification and the reusability for every product.
Mm-hmm. What kind of inference engine do you use for checking the changes in your models? Is there something that has if-then-else rules, or something else that can detect that this was changed, or just if some data was changed, you say it's changed?
No, when we check in the new version of a CAD model, then we start a process which checks the XML file, which was exported during the check-in, and we compare this XML file with the previous version. Then
like text to text, or semantically what's in there?
Semantically. So we have to check semantically because we have the main problem is the replace scenario, because we might have changed the position of one connector to another area of the wiring harness. Therefore, we have to check it semantically. Line by line wouldn't work, because then we wouldn't see the replacement scenarios.
Nice. Just one comment about your paper. If you have research questions at the beginning, and you have how to change in CAD data of wiring harness, how can relate the changes, and so on, it's good practice to have a discussion or to have an outlook in which your questions are reflected and answered in some sort, because in your paper one have to go back to the paper to see where each question was resolved or answered. That's just a good practice. It's not something that you did wrong. Just comment.
Yes, it's a really good point. Thank you for that.
Okay, thank you, everybody. If anybody have any questions for anybody else, please ask. Or be silent forever. You will be married for the rest of your life with knowledge and usage of knowledge. Okay. Again, thank you all. Thank you, our helper. We will now do our.
I have. Sorry to interrupt. I have one remark. It's not a question, but I would like to congratulate the authors of the 5th paper because they received the Reviewer's Favorite Award. Just to make that clear, that means that you're in the top 10 papers ranked by the reviewer score. So congratulations.
Oh, yeah. Nice. Well, thank you all. Have a nice rest of the conference. I hope I will see you in 2 years in Cavtat on the coffee on a sunny day. Bye-bye.
Bye-bye.
Bye. Have a nice
Bye.
day.
Thank you very much.